Two passwords get stored in two databases. One database leaks tonight. The attacker cracks every password in minutes. The other database leaks tonight too. The attacker walks away with nothing for the next 200 years. Same password, same hardware, different hashing choice. Today, we visualize exactly why that gap is so enormous. Let us start with the definitions, because this is where most developers go wrong. MD5 is a general-purpose hash function from 1991. It was built for speed. The job is file checksums and integrity verification. Bcrypt is something completely different. It is a password hashing function from 1999. It is deliberately slow. The job is storing credentials safely. Look at the outputs side by side. MD5 gives you 32 hex characters, the same answer every single time. Bcrypt gives you 60 characters, and the answer changes every time you run it. A hash function is not the same thing as a password hashing function. Here is why this matters in 2026. A single modern graphics card can compute over 100 billion MD5 hashes per second. Stack 8 of them in one rig, and you cross the trillion mark. Watch what happens when we point hashcat at an 8-character MD5. The key space looks huge on paper, but the cracker chews through it in under a second. By the time you finish reading the password, the attacker has already moved on to the next one. So why is MD5 so fast? Because that was the entire point. In 1991, Ron Rivest designed MD5 to fingerprint files. You wanted to know if a software download matched the original, you ran MD5 on both and compared. Speed was a feature. It needed to scan gigabytes in seconds. Then developers reached for the nearest hash function in the standard library and used it on passwords. The very property that made MD5 great for file integrity made it catastrophic for credentials. Speed is now the attacker's gift. In 1999, two researchers named Niels Provos and David Mazieres looked at this mess and proposed the opposite philosophy. They built Bcrypt. Bcrypt is intentionally expensive. It is slow on purpose. It is wasteful on purpose. Every cycle the attacker has to burn is a cycle that protects your user. Bcrypt is the antithesis of speed, and that is exactly what makes it useful. Bcrypt has a knob called the work factor. You can see it baked right into the hash string itself. A work factor of 10 means the algorithm runs 2 to the power of 10 internal iterations. A work factor of 14 runs 2 to the power of 14. Every time you add 1 to the work factor, the cost doubles. So a cost of 14 is 16 times slower than a cost of 10. You decide how much pain you're willing to inflict on yourself and on every attacker who steals your database. Now point that same monster graphics card at Bcrypt instead. The numbers fall off a cliff. From 100 billion hashes per second on MD5, you drop to a few hundred on Bcrypt at cost 12. That is not a typo. We went from 11 zeros down to 3. The same silicon, the same power draw, billions of times less progress. Bcrypt did not get faster hardware. Bcrypt refused to cooperate with the faster hardware in the first place. There is a second problem with MD5 that has nothing to do with speed. MD5 is fully deterministic. The same input always gives the same output. So if 1 million users in a leaked database pick the password letmine, every single one of those rows has the exact same hash. Attackers exploit this with rainbow tables. They pre-compute the MD5 of every common password once, share the table around the world, and then crack millions of accounts in a single lookup. Bcrypt fixes this by baking a random salt directly into the hash. Every time you hash the same password, you get a completely different output. The salt is stored right inside the hash string, and the algorithm reads it back when it verifies a login. There is no pre-computation an attacker can do because the salt was not known to anyone until the exact moment your user signed up. Put the two side by side, and the rainbow attack tells a clear story. Against the MD5 database, the lookup is instant. The attacker compares stolen hashes to the pre-computed table, and the matches drop out like coins from a slot machine. Against Bcrypt, the same attack returns absolutely nothing. Every salt is different, so every hash is different, and the rainbow table is worthless before it even starts. Now imagine the attacker gives up on rainbow tables and just brute forces. An 8-character MD5 password falls in minutes on a single rig. Make it 10 characters, and it falls in hours. Now switch to Bcrypt at cost 12. The same 8-character password would take centuries to brute force on the same hardware. Not years, centuries. The user can pick a mediocre password and still sleep peacefully through the breach. You might think the attacker just buys more graphics cards. For MD5, that works perfectly. Double the cards, double the hashes per second, all the way up. For Bcrypt, the math breaks. Bcrypt deliberately uses 4 kilobytes of memory per hash and constantly shuffles data inside that buffer. Graphics cards are terrible at this. They have thousands of tiny cores, but very small per-core caches. Add more cards, and you slam into a memory bandwidth wall, not a compute wall. The returns diminish fast, and then stop entirely. Translate that into actual dollars. To brute force a single 10-character Bcrypt hash at cost 12 with current hardware and current electricity prices, you're looking at roughly $100 million in compute and power. For one password. For one user. Compare that to MD5, where the same crack costs you the price of a coffee in cloud GPU time. Bcrypt does not just slow attackers down. Bcrypt bankrupts them. And yet, in 2026, MD5 is still everywhere. Old PHP forums, internal tools nobody wants to touch, vendor systems where the migration plan never made it past the wiki page. Every single one of these is a breach waiting to be sold on a forum. The technical debt is not just messy code. It is a direct line from a database leak to your users being phished 6 weeks later when their reused password works on 12 other sites. So how do you pick the right work factor today? The rule of thumb is simple. Tune Bcrypt so that a single hash takes around 250 milliseconds on your production server. That is slow enough to be painful for an attacker, fast enough to keep your login endpoint responsive for real users. Measure it on the real hardware, not your laptop. Reevaluate every 2 years as hardware gets faster. And never ever hash passwords with anything from the MD5 or SHA-1 family. Bcrypt was the answer in 1999. It is still good in 2026, but the world has moved on. The current state of the art is Argon 2ID, the winner of the 2015 password hashing competition. Argon 2ID is memory hard, which means it forces the attacker to spend not just compute, but also large blocks of memory per single guess. Graphics cards and custom silicon struggle even harder with memory bandwidth than they did with Bcrypt. If you're picking a hashing library for a brand new project today, Argon 2ID is the modern default. Bcrypt remains a perfectly acceptable second choice. So here is the whole story in one breath. MD5 is a fast file fingerprint that was never meant for passwords. Bcrypt is a slow lock that was. The difference is not academic. It is the difference between an attacker walking through your front door in seconds and an attacker giving up before their grandchildren are born. Pick the right tool, tune the work factor, plan your migration to Argon 2ID, and your users will never know how close they came.